Take a close look at this structure. With its intricate metallic ridges and glowing spiral cores, it looks like something you'd pull out of an alien spacecraft, or perhaps a microscopic biological organism viewed under a powerful electron microscope. But you can't actually touch it because it doesn't physically exist. Every curve, crevice, and valley here is generated entirely from pure, raw mathematical data. Shapes like these are known as fractals. A fractal is a never-ending pattern created by taking a single, simple mathematical equation and running it on a loop, over and over again. When we run these repeating equations through powerful computers, we can visualize geometric boundaries that were previously impossible for the human mind to picture. For decades, the most famous example of this math was the Mandelbrot Set. It has a very specific defining characteristic. You can zoom infinitely deeper into its borders, and the exact same pattern will just keep reproducing itself. There was, however, an obvious catch. No matter how deep you go into the Mandelbrot set, you are completely trapped on a flat, two-dimensional plane. Mathematicians and computer scientists spent years trying to figure out what this exact shape would look like if it popped off the page into three-dimensional space. It turned out to be incredibly difficult. You couldn't just extrude the flat image like a block of clay. The moment anyone tried to introduce a z-axis to give it true depth, the math collapsed into a blurry smear. The persistent failure to find a working 3D version exposed a gap in multi-dimensional mathematics. The rules governing 2D surfaces couldn't yet account for the recursive complexity of a volume. So the solution eventually came from an unlikely place. In the late 2000s, a community of amateur mathematicians collaborating online figured out how to bypass the roadblock by using spherical coordinates, essentially wrapping the math around a 3D globe. With a sense of awe, that mathematical workaround finally generated the exact 3D shape they had been searching for, the Mandelbulb. Because it exists in 3D space, the mathematical structure folds endlessly into itself. It continually generates microscopic, detailed topography right out of thin air. By pulling the equation off the flat page, these coders manage to add a physical dimension to the concept of infinity. Actually displaying this endless detail on a normal computer screen poses a technical challenge. Traditional 3D graphics use a mesh of flat polygons to build shapes, which works fine for video games, but cannot process a surface with infinite microscopic details. To solve this, computers use a rendering technique called ray marching. Instead of drawing flat shapes, the computer shoots a straight line, a ray, forward into an empty void, taking progressively smaller, measured steps until it hits the exact mathematical boundary of the equation. The exact moment that ray makes contact, the computer calculates how a light source would bounce off that invisible boundary, automatically painting the intersecting point with shadows and highlights. The resulting metallic, biomechanical look of the Mandelbulb is the direct visual translation of the underlying math. Those shadows and highlights are the output of raw geometry reacting to simulated light. It raises an obvious question. Why does cold computational logic so closely mimic the biological textures of living things? When you look closely at macro-botanical growth in the real world, you see the same patterns. Every individual cone on a Romanesco broccoli is a miniature copy of the entire vegetable. That exact same recursive logic, a shape continually folding out of itself, dictates how a fern frond unfurls on the forest floor. The logic scales internally, too. Our own blood vessels use this branching, fractal rule to maximize surface area and deliver oxygen efficiently within the confined space of the human body. Expand the scale outward by millions of light years, and you'll find the identical repeating spirals dictating the outer arms of entire galaxies. The recurrence of these patterns across broccoli, ferns, and galaxies suggests that recursive math is a common solution for building complex structures. It allows for the packing of immense surface area and intricate detail into finite spaces. By finally rendering these 3D fractals on our computers, we have built a digital sandbox where we can hold, manipulate, and observe that underlying operating code. It reminds us that behind the complexity we encounter in the world, there is often just one simple rule running on an endless loop. The chaos and beauty of the natural world, in the end, is really just mathematics made visible.